students join and we'll start the session. Okay.
Yes, sir.
Okay.
So will these slides be shared with us?
Yeah, these all with the slides will be shared usually. It will be available in your supplementary sections. Okay.
Yes, I yes, I should.
Um, Hello everyone. So can we start the session now or wait for 2 more minutes?
So we can start.
Okay. So we'll see the main algorithms which were used on week 11. So my screen is visible, right?
Yes,
Yes,
sir.
sir.
Yeah. The first one we'll see is Dijkstra's algorithm. So in this, we'll find a shortest path from a source vertex. So we'll find the shortest path from one vertex to every other vertex. But this is an important point. There can't be any negative edge weights. So if there is a negative edge weight, Dijkstra might not work. Okay, this algorithm might not work. So what is negative edge weight? Can someone tell me?
Sir, value is in minus.
Yeah, exactly. The
Two
weight
values.
weight of an edge is a negative. That's it. So there can't be any negative edge weight in it. Not even one can be negative. Okay. So if that is the case, then Dijkstra might not work. So yeah, we'll see the second one, which is Bellman-Ford algorithm. So this is also similar to Dijkstra. So we'll find the shortest path from a fixed source vertex to every other vertex. See, but in this case, it can or cannot have negative edge. It will work in both cases, but it will not work in negative side. So can someone tell me what is the difference between these two, the Dijkstra and Bellman-Ford?
You
Sir,
can use it
the
even when
value
there
of
is
age
negative.
cannot negative in Dijkstra algorithm and in Bellman-Ford algorithm can negative age value but cycle do not.
So what is a cycle basically?
Sum of age of cycle cannot be negative.
Yeah. So what is a cycle basically?
Uh,
Two vertices.
Vertex repeating.
Yeah. So and there must be at least three vertices, right?
Yes, sir.
Yeah. There must be at least three of them which are repeating. For example, let's say this is one, this is two, and this is three. Okay. So we'll just join all these three. Okay, let's take this is 4 and this is -1. So what can be the possible edge weight of this such that Bellman-Ford works? Can someone tell me the range of this?
Greater than 0,
Okay, so one told me it is greater than 0. So what are the other possibilities?
and it should be lesser than 3.
I'm talking about only this value, right? It should be
Okay,
greater than 0 and less than 3. So what can be, I'm asking what can be the possible edge weight of 1 to 3? This edge, right? So what can be the possible weight of X so that Bellman-Ford works?
uh,
So I got one answer as X is greater than 0. So what are the other possible answers? Can someone unmute and tell me? First, did you get my question, everyone?
Yes, sir. It should be greater than -3.
Yeah, it should be greater than -3. Okay.
Greater than or equal to.
Yeah, exactly. So it can be greater than or equal to -3. So that will be the correct answer, because if you see, if you come from 1 to 2 and 2, so this edge weight would be 3, right? But again, if you go from 3 to 1, what happens? So 3, let's say this can be negative also. So let's say 3 minus x, it should be greater than or equal to 0, right? So it can't form a negative cycle. So x, just a minute. Yeah. So x should be lesser than or equal to, sorry. So this is minus, just a minute. So lesser than or equal to 3.
There is no upper bound.
Sorry. So this is the minimum value that it can take, right? Sorry.
Yes.
I mean, what I'm trying to say is, just a minute. So 3 plus x, right? 3 plus x should be greater than or equal to 0, because we are adding all this weight, right? So 4 plus -1 plus x. This can't be negative, right? Basically, this is what Bellman-Ford says. The loop can't form a negative edge weight, correct?
Yes, sir.
So x should be greater than or equal to -3 will get, correct?
Yes, sir.
Yeah. So this is the possible value of x. The weight can be greater than or equal to -3. So everyone got this? Why it is greater than or equal to -3 in this case?
Yes, sir.
Yeah. Okay. Just a minute. Yeah. So, and this is the third algorithm we are going to see, Floyd-Warshall's algorithm. It will say all pair shortest path with or without negative edge weights. See, it is similar to Bellman-Ford. It can have negative edge weight, but there can't be any negative cycle. Okay. So, and it will compute shortest path between any two vertex. You're getting it?
Yes, sir.
Yeah. This is what Floyd-Warshall algorithm do. And can someone tell me what is MCST?
Minimum cost spanning tree.
Okay, so it is minimum cost spanning tree. So the algorithm which we will be used to find this is Prim's and Kruskal's algorithm. So we'll see every one in detail right now. So these are the algorithms that we are going to learn in this session, and we'll also solve one question regarding that. So can we proceed to the next slide now?
Yes, sir.
Yeah. And if you guys have any doubt in between, you can just unmute and ask.
Sir,
Yes.
all pair sorted path means
All pair shortest path means, let's say a graph has 1, 2, 3, 4 as the vertices. So it will give us what is the shortest distance between any 2 points. Just take any 2 points. Let's take 1 and 3. It will give what is the shortest distance between 1 and 3. And if you want to take 3 and 4, it will give the shortest distance between 3 and 4 also. You're getting my point?
yes, sir.
Yeah. So that's what it means. But in these two, like we have to first say our source vertex. So we should say we are starting from 1. Then what will happen? So what is the shortest distance between 1, 2, 1, 3, 1, 4 only? So it will not say what is the shortest distance between 3 and 4. You're getting my point? If you
Yes,
take
sir.
vertex as 1, it is same for both the cases. I mean for Dijkstra and Bellman-Ford. Okay?
Yes, sir.
Yeah. So we'll proceed to the next slide now. Yeah. So Dijkstra algorithm is used to find the shortest path from a fixed source vertex to every other vertex in the graph. So as I said, if the vertices of the graph are 1, 2, 3, 4, and 5, and we say our source vertex is 1, so we can find the shortest distance between 1 and every other vertices. You are getting my point? Hello?
Yes, sir.
So it is applicable for weighted graphs with positive edge weights. So the edge weight can't be negative, and it is not. Yeah, the second point says that it is not applicable for graph having negative edge weights. Even if one edge weight is negative, we can't apply this algorithm. It may or may not give the correct result. Okay, so we'll see what the algorithm does. We'll start with the source vertex. So we'll consider any one vertex as the source vertex. Okay, so let us take the vertex as I. We'll initialize the distance of a vertex I to 0. So we'll just initialize 0 to the vertex I and infinity to every other vertex in the graph. Okay, and then what we'll do is we'll update the distance values of neighboring vertices of I. So what are the neighbors of I? We'll just check that and update its distance. So what is the weight given? So we'll update accordingly. And every time every time a new vertex is visited, so we'll just visit one other vertex, new vertex will be visited. We'll update the minimum distance values of its neighbors. So there will be two values. Already there will be one value. Let's say, just a minute. I'll just share my board now. So let's say, suppose what it means, suppose let's say this is 5 or something. Okay, and so this is 1, 2, and 3. So what we'll do, we'll take this will be some distance, right? K, and this will be some distance A, right? Hello. 1 to 2 and 2 to 3 will be some K, and 1 to 3 will be A, right?
Yes, sir.
Let's assume like these are the distances. So we'll pick the minimum of these two and put it here. Okay. Let's say K is the minimum. We'll write the distance to be K in this case. 1 to 3 would be K. Okay. Assuming that our initial source vertex is 1 and K is the minimum distance. Okay. From K, and this is A. This is A. Okay. So assuming that K is minimum and 1 is the source vertex, we'll put the distance from 1 to 3 as K because that is minimum of K. Okay. You got this point?
Yes, sir.
Yeah. So this is what we'll do. We'll just go with the first question now. An undirected weighted graph G is shown below. Okay. So find the set of all possible integers of x such that we can use Dijkstra algorithm. The length of the shortest path from A. So the source vertex given here is A to the vertex J. So we have to reach this vertex is less than 13. Okay, it is strictly less than 13, not less than or equal to 13. So everyone got this question. So we have to apply the Dijkstra algorithm starting from the source vertex A. Okay, and then we have to proceed. We have to reach J such that the distance should be less than 30, and this is the value of x. They're asking what can be the possible values of x. So everyone got this question? Hello?
Yes, sir.
Yeah. If you guys have any doubt, just unmute and ask. For students who have joined late, if you want me to explain once again the Dijkstra algorithm or something, just let me know. And as I said, to solve this question, what you have to do is you have to apply Dijkstra algorithm from source vertex A, and you have to try to reach J. Okay, and it is given that the shortest path from A to J is less than 13. So it can be anything less than 13. So what can be the possible values of x is the question which is asked. If you guys have any doubt, you can unmute and ask. And if you got the answer, just post the answer in the chat box. So am I clear?
So is it possible to explain?
Which one? Or only the Dijkstra algorithm or from the starting?
For this sum, for this algorithm.
Okay. You mean just a minute? This slide or this slide?
I joined it late, so I'm sorry about that.
Okay.
I did not catch the introduction in the beginning.
Okay. So I'll just come once again. So in this session, what we'll be doing is we'll just look at the main algorithms which are used on week 11. So the first thing is Dijkstra algorithm. So it is used to find the shortest path from a fixed source vertex. So let's say a graph has n vertices. So we'll just say we'll just take one vertex at random. So we'll just say for example vertex 5. So from vertex 5, we have to find the shortest path from 5 to 1, 5 to 2, 5 to 3, 5 to 4 till 5 to n minus 1. We have to find all the shortest path. Okay, starting from 5. So that will be we can find it using Dijkstra algorithm. But in this case, there can't be any negative edge weight. So you know what is a negative edge weight? Hello.
No, sir.
Yeah. So basically, what is a weight of a graph? What is edge weight basically? Okay, we'll see. Let's say this is 1 and this is an edge between 1 to 2. Okay, so usually like we have studied an undirected graph. Now we are going to associate a weight or cost to them. Let's say this is 20 is given. Okay, this is a positive edge weight. So it can mean anything. For example, let's say this is a station A and this is a station B. Okay, and this 20 may represent the distance between them in kilometers. Okay,
Okay.
so this is an edge weight. Okay, this edge has a weight, right? 1 and 2. Like there can be any edges which can have a weight or cost associated with it. So
Okay.
what it means this one which is given here, a number which is given here, this can't be negative. Okay,
Okay.
that's what the one of the condition to use the Dijkstra's algorithm. So the edge weight can't be negative. Okay, if
Okay.
edge weight is negative, we can't apply this algorithm. So yeah, for the second one, it says it is similar to the Dijkstra, but what the subtle difference between these two is it can have negative edge weight also, but negative cycle is not possible. So can you tell me what is a cycle?
So
Repetition of edges.
Yeah, so basically like cycle means it'll repeat the vertices, right? Minimum 3 of them, like this forms a cycle, right?
pointing to them, sir. Yeah.
Yeah, but we won't say this is a cycle. So sorry, this is not a cycle. Okay, but minimum 3 vertices should be there and they form a loop. So basically that is a cycle. Okay.
So you're sharing something because we're seeing the algorithm right now.
Yes, sir.
Okay. Sorry.
Not able to see.
Yeah, now is the board visible?
Yes, sir.
Yes.
So just a minute. So I mean, some are solving the question. I'll just show them the question. Those who are solving it, just take a screenshot of it if possible. So this is a question. So if you want, just take a screenshot of it. Okay. Yes. So my whiteboard is visible, right?
Yes, sir.
Yeah. So this is a cycle. Okay. So let us like put some weights to this. Let's say this is 3, and negative edge weight is also possible for Bellman-Ford, right? That's what we saw.
Yeah.
Weight can be negative also. Let's take this is -2. Okay. So let's take this is x. Okay. So if you add all these three, this should be greater than or equal to 0. Okay.
Okay.
So add all these three, what will you get? 3 minus 2 plus x is greater than or equal to 0, right? This is what you should get.
Yeah.
This is a condition. It can't be negative. Okay. So 3 minus 2 is 1 plus x greater than or equal to 0. So what can be the possible values of x? Can you tell me?
-1.
X is?
-1.
Yeah, like can you tell me in inequality?
So less than, greater than equal to -1.
Yeah, x is greater than or equal to -1 are the possible edge weights which it can have. Suppose it is -5, then we can't apply this algorithm here. You get it?
Yes, sir.
Yeah. So that's what Bellman-Ford says. and then just a minute. We'll come to the next one. So Floyd-Warshall algorithm, what it does means it'll like just a minute. I'll just again use the board. Yeah. Let's say there are n vertices. Okay. In what Dijkstra and Bellman-Ford does is, it will take one source vertex. Hello.
Yes, sir.
Yeah. What it will do is it will take one source vertex and let's take 3 as the source vertex, which is initial starting vertex. It will tell what is the minimum distance between 3 and 2, 3 and 1,
For each of them.
3 and 4, 3 and 5, up to 3 and n. Okay. This is what both Dijkstra and Bellman-Ford.
Bellman.
Okay. So what Floyd-Warshall does is it will take any random two vertices from this. Let's take 4 and 5. It will give me the shortest distance between 4 and 5 also. Let's take anything like 7 here, 7 and 3. Let's take any two vertices. So it will give the shortest distance between 7 and 3 also. You get it?
So it is a subset or a small?
No. See, it is all pair shortest path. You're getting it? See, but what will Dijkstra and Bellman-Ford does? It will give the shortest distance between. See, Dijkstra and Bellman-Ford gives the shortest distance between a source vertex and another vertex. But here, in this case of Floyd-Warshall, it will give the shortest distance between any two vertices. Okay?
Okay.
You get it? If you take any two vertices in the graph, you will get the shortest path if you use this algorithm. Okay? Yeah. And similarly, it is similar to Bellman-Ford, but it can have negative edge weights, but no negative cycle is possible. If you say negative cycle, then that's no meaning of shortest path itself, because you can just go to that loop and again come to some more negative weight, right? Yeah. So negative, in context of negative cycle is there, we can't talk about shortest path itself. So what is MCST? This one. MCST is minimum cost spanning tree. Okay. So we'll learn about it. So we can find the minimum cost spanning tree using Prim's and Kruskal's algorithm. So these are the algorithms that we are going to see in this session.
Okay, sir.
Okay. So yeah, the first we'll talk about Dijkstra algorithm. So it is used to find the shortest path from a fixed source vertex to every other vertex in the graph G. So yeah, as I said, we'll just pick one vertex. Just a minute. We'll just pick any one vertex. In this case, we picked 3, and we'll find the shortest path between 3 and 2, 3, 1, 3, 4, 3, 5, 3, 7, and 3 n till 3 n. Will the shortest path. Okay, that's what it says. So yeah, these two conditions must be applied. For example, it is applicable for weighted graphs with positive edge weights, and edge weight can't be negative. So these are the 2 points which we discussed. Okay, so this is the algorithm basically. We'll start from the source vertex I. So in this case, the source vertex is 3. Okay, and from 3, we'll check all the possible neighbors. So that is the second point given. See, initialize the distance of vertex I to 0 and rest to infinity. So what we'll do, we'll initiate this to 0 and rest of all to infinity. Okay.
Okay.
We'll put rest of all to infinity. But see, basically the graph can also be like this one. Let's say this is 3, this is 1, this is 4. We'll just assume that. Okay, so this will be 0 and this will be infinity and this will be infinity. Okay. And what we'll do is update the distance value of neighboring vertices of I. So we'll just update the neighboring vertices. So let's say this is 4 and this is 5. So the neighboring vertices of 3 is 1. So this will be 4 instead of infinity, right? So which is minimum? Infinity is minimum or 4 is minimum?
4.
So 4 is minimum. So that is what said in the last point. So each time a new vertex is visited, update the minimum distance of its neighbors. So if we go by distance, it is 4, but initially it is assumed as infinity. So minimum of 4 and infinity is 4. So we'll take it as 4. Now we can go from 1 to 4, right? in the and the distance between them is 5. So
Yeah.
what we have to do is we should not write 5 here. This should be 5 plus 4 because we are traveling from 0, right? So
Yeah.
we'll just add these two. So 5 plus 4 will give us 9. Okay. And we have to find what is the minimum between 9 and infinity. So minimum of 9 and infinity would be 9.
9.
Yeah. So now we can say that from 3 to 1, the minimum distance is 4, and from 3 to 4, the minimum distance is 9. So this is how Dijkstra algorithm works. This is a really simple example of that. So yeah, once we solve this question, we'll see how this is solved.
Okay, sir.
Yeah.
Thank you.
Yeah, this is the question. I hope everyone solved this, or you guys need like 2 more minutes. Hello, can I discuss this only?
Yes, sir.
Yeah. So everyone saw this question, right? While I was explaining the concept, you guys took a screenshot or something. So do you want me to wait for 2 more minutes? I can. If you want, I can also discuss the solution. Okay, I'll discuss it. Sorry,
Yes, sir, you go ahead.
wait for a minute. Okay, I'll just wait for I'll just start discussing at 8:33. So yeah, can we discuss the answer now?
Yes, sir.
Yeah.
Yes, sir.
Okay. So we'll see what we have to do. Just a minute. Yeah. So first, what we'll do, we'll just remove the edge BE from the graph and then find the shortest path from vertex A to every other vertex. So yeah, we'll just remove this one, this edge B to E, and we'll find the shortest path from A to every other vertex using Dijkstra. Okay. So yeah, starting from the vertex A, as it is the source vertex, initialize the distance to 0 and infinity to other, as we have discussed. So this thing will be 0 and the rest would be infinity. Okay, so just a minute. Yeah, we can see from the figure. So the board, the slides are visible, right?
Yes, sir.
Yes, sir.
As you can see, we have removed the edge B to E, and we have initialized the source vertex to be 0 and the rest to be infinity. So yeah, so which one will be reached first? Is it the value B, I mean the node B, or vertex D?
D.
Yeah, since this is the shortest path, right? So first this will be reached, right? So what? So now tell me, what is the minimum between 1 and infinity?
1.
Yeah.
1.
So D will be initialized to 1, right? Just yeah. See, use
Yes.
the algorithm, update the distance values of each of the vertex in the graph that are adjacent to it. So adjacent to A are B and D. Okay, which will be the shortest distance from vertex A in terms of weight. In terms of weight, we can see D is the shortest, So yeah, we'll just update the distance from infinity to 1, right? And what will be this distance? It will be 2, right?
Yes,
Correct?
Yes, sir.
Yeah. So now we know that we can travel from D to B, A to B in A to D and D to B, and or directly we can travel from A to B. Okay. So now what happens? We know we have also we can also go to B directly. So we've updated to 2. Okay. Now what will happen if we come from D to B? It will be 5 plus 1 6, right?
yes, sir. Bigger
Yes, sir.
than 2.
So now what we have to do? We have to find the minimum of 6 and 2, which is the minimum between 6 and 2,
2.
right? Yeah. So it will remain same. The 2 will remain same. It will not be updated to 6. Okay. Now what happens? We have to go to C. What is the neighbor of B? We can see it is C, right?
Yes,
Yes, sir.
So what will happen? It will be 2 plus 4, right?
4, 6.
Yeah. So C will be 6. So minimum of again 6 and infinity will be 6. From C we can go to E, H, correct? So now
Yes,
let me, what will be
Yes, sir.
the H value right now?
14.
8 plus 6, 14.
And then E.
6 plus 3, 9.
9.
So this will be 14 and 9 respectively. Okay. From E you can see. So first we'll go to E because it is the shortest. From E we can go to G and H. But see, if we go to H, what happens? What will be the value of H if we go from C to E and E to H?
It'll be 13. Lesser than
So the minimum between 13 and 14 would be 13, right?
13.
So this 14 will be updated to what? 13. Everyone get this? And what will be
Yes.
the value of G, which will be G will be
10.
10.
10 and
Yeah,
F
30.
will be
Yeah. So first
15.
see. So first we changed G to 10. Since we are traveling, which is the minimum of minimum weight. So we are going to G, which is 10 here. So and then see, initially like it can be 13, but what happens if we go from G to H? What
It's
happens?
even less.
It will be even less. So it will be 12, right?
Yes, sir.
Yes, sir.
So this will be updated to 12. Okay. From 12, we can go either to I mean J or I. So in both cases, like we'll just travel to any one of those. Okay. So, but what is the question which is asked? The shortest distance between A and J only, right?
Yes, sir.
13.
Yeah. So what will happen if we go from H to J? It will be 13, right? Infinity will be correct.
Yes, sir.
And even this will also be 13. Okay.
Yes.
So both of them will be 13. But in the question, it is said that the distance between A and J is less than 13, strictly less than 13, right?
Yes.
Yes, sir.
It is because of this BEH, correct?
Yes, sir.
If we can find a way to travel, if we find a way to travel to BE with a lesser weight than what?
13.
13.
Oh. Oh.
See, so what is the distance between A to E now currently?
2 plus x. Like currently
Nine.
it is 2 plus 4 plus 3. 9.
See, we have already calculated, right? That is nothing but this one. That is what we have calculated.
Yes,
So
sir.
now we know that from A to all other vertices, this is the shortest path with the given edges. So now we are going to add an edge. Okay, the one which we have removed, we are going to add it now. Okay. So we know
Yes,
that
sir.
A to E we can reach in the minimum distance of 9. Okay. So we are adding an edge from B to E. This B to E should be less than 9, right? It is not less than 9. If we go from A to B and B to E, the whole thing should be less than 9, right?
Yes, sir.
So A to B is already given as 2. So what can be B to E then? 7, right?
Yes, sir.
Everyone got this?
Yes, sir.
E should be less than 9. From A to E, we can go to A to B and B to E also. So because this B edge is the one which is missing. So A to B already is given the minimum distance is 2. And from A to E, it is given the minimum distance is 7. So there is an edge connecting these two directly. This whole thing, A to B and B to E, should be less than 9. So from that, we'll get this X value as 7. So everyone got this?
Yes,
It will
sir.
be less than 7, no, sir?
Yeah,
Okay, okay. Sir.
it should be less than 7. Correct? Because 7 plus 2 will get it as 9. See, that's what we are going to see. See, so we can see that this is the shortest path without that BEH. Correct? This will
Yes,
be
sir.
But it is not shortest because in the question it is given the shortest path is less than 30, right? So it is
Yes.
because of this BEH. Okay. So yeah, from that we can see the length of the path from B to E is 7, because like A to B we can go in the distance 2, and B to E it is given as 9, but it must be less than 9. Therefore, X must be less than 7. Okay. So the
Yes, sir.
inequality basically would be X plus 2 is less than 9 and X is less than 7. So what are the possible values of when if X is less than 7? What can be the possible values?
1, 2, 6.
1, 2, 3, 4, 5, 6.
Yeah.
0, 1, 2, 3. Oh, 0 can't be possible.
Correct.
Yes,
So
sir.
1, 2, 3, 4, 5, 6. Till that it is possible. Okay. It can't be negative also because we are using Dijkstra here. Okay.
Yes, sir.
Yeah. Because they are asking positive integers, therefore 0 will not be included. Okay. So this is the correct answer. So 1, 2, 3, 4, 5, 6. Which is option? Which option? Just a minute. Option C or option B. Okay. So I think most of you got the correct answer. Yeah. Almost everyone got the correct answer. So can we move to the next question now? Is this concept clear?
Yes, sir.
Clear, sir.
Yes, sir.
So this is the second one. A company has branches in each of 5 cities, C0, C1 to C4. Okay. The fare it is in 1,000 rupees. So 4 means 4,000, 2 means 2,000 basically. Okay. For a direct flight from CI to CJ. Okay. It is given by the I, jth entry in the following matrix. So this is an adjacency matrix. Correct? Hello?
Yes, sir.
Yes, sir.
You guys know how to draw the graph if the adjacency matrix is given?
Yes, sir.
Yeah. Okay. So what are the vertices of this graph?
C1, C2 up to C4.
Up to C4, right? So you have to draw and this is C0. It is C0 to C4. So this is C0, C1, C2,
Yes,
C3,
sir. C0.
C4, and C0, C1, C2, C3, C4. Okay. And C0 to C1, there is an edge and its weight is 2.
2.
Okay. Yeah. Similarly, C0 to C4, there is an edge and its weight is 4. Okay. This is what it means. So everyone first draw this graph, and an employee of the company wanted to travel from city C0 to C3. If she traveled by the cheapest route possible, then the total fare that she paid. So basically, we have to draw the graph of this of the given adjacency matrix, and then we have to find the shortest distance between C0 to C2. You can use any one of the algorithm, like you can use any 3 of the algorithm if you want, Dijkstra, Bellman-Ford, or Floyd-Warshall. So basically, you have to find the shortest fare between C0 to C3. Okay. So first you just draw the graph and then find the shortest path. And write your answer in the chat box. For example, like if you got 10 as the answer, then enter 10,000. Okay.
Yes, sir.
Okay. If you guys have any doubt, just unmute and ask me at any time. I request everyone to at least draw the graph of this, because the next question is also a similar question. The adjacency matrix is same. So yeah, just draw the graph of this at least, if you don't get the answer. By the way, everyone knows how to draw this graph, right? Of the given adjacency matrix.
Yes, sir.
Okay. Hello, is anyone still solving? You want me to explain this? Okay, you don't know how to plot the graph. Okay. So you want me to explain how to plot this graph? Okay, yeah, we'll see while doing the solution. Okay. Yeah, like while discussing this solution, I'll just let you know. So what about others?
Yes, sir. I
Can I
got
discuss the solution now?
yes, sir.
Yes, sir.
Yeah, so everyone got the correct answer. The correct answer is 6,000. Okay, so we'll see. So we'll first draw the graph of the given adjacency matrix. So this will be the graph. So how to do this is, see, so there will be 5 vertices basically, C0, C1, C2, C3, C4. Okay, see, you can see that C0 and C1 are connected with the h weight 2, right? Hello?
Yes, sir.
Yes, sir.
Yeah. So C0 and C1 are connected with h weight 2, and C0 and C4 are connected with h weight 4. So C0 and C4 are connected with h weight 4. So the rest are infinity, C2 and C3. This basically means there is no direct edge between C0 and C2 and C0 and C3. Okay. So now we have drawn it for the C0. Now we'll go to C1. See, from C1 to C0, there is an edge of weight 2, which is already drawn. So C1 to C1, it is 0. So C1 to C2, there is an edge. From C1 to C2, see, you can see this edge, right? There is an edge and it is of weight 3. Okay. Similarly, from C1 to C3, there is a direct edge of weight 9. This is the other edge. And C1 to C4, there is no edge. Okay. So everyone getting it how we are drawing this graph?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yeah. Like 2 people. So everyone got it right. So if anyone of you don't get it, just let me know. Stop me in the middle and let me know. See, for C2, what we are just okay. For C2, so this is the vertex C2. From C2 to C0, there is no edge, so it is infinity here. From C2 to C1, we can see there is an edge of weight 3, which is already drawn. So C2 to C2 to C2, the edge weight is 0 because there is no edge 2 itself. So C2 to C3, there is an edge weight 1. So C2 to C3, there is a direct edge and its weight is 1. And C2 to C4, if we can see, there is an edge and its weight is 5. Okay. Similarly, we are drawing it for C3 and C4 and we will come up with this following graph. So everyone got how we got this graph?
Yes, sir.
Yes, sir.
If any one don't know how to draw this graph, you can just ask me once again. Okay. Okay, I'll proceed then. Okay. So now we are going to use Dijkstra algorithm starting from the vertex C0. Okay. So because we want to find the minimum distance between C0 and C3, right? So we'll start applying Dijkstra algorithm. So what will be the first one which will be updated? It will be C1, right?
Yes, sir.
Because that is the shortest distance and this will be 2, right?
Yes, sir.
Yeah. What will be the second one which is updated?
C4. That will be
C4.
4.
C4.
C4 will be 4. So we can see. So the first one will be C1, which is 2. The second one will be C4, which is 4. What is the next one which will be updated?
C2.
C2.
C,
C2.
which will be 2 plus 3, 5.
5.
Right? Yeah. So this
Yes.
will be 5. And what will be the next one which will be updated?
C3.
C3.
C3, right? So which
Yes.
will
2 plus 3 plus 1 plus 1.
yeah,
6.
which is 5 plus 1, 6. Correct? So
Yes,
this
sir.
will be the final result after applying Dijkstra algorithm starting from the source vertex C0. Okay?
Yes.
Yeah.
So
So
this is not a planar graph. So there is an intersection of the edges.
no, you can draw the edge from C4 to C2 outside edge, right? Outer edge can be drawn. Okay.
Yes.
So this is a planar graph. You can draw an outer edge from C4 to C2. Okay.
Yes.
Yes, sir.
So this is the shortest path: C0 to C1, C1 to C2, and C2 to C3. So the what is the shortest path weight is 6. Okay. So the answer would be 6,000.
So it does not matter if it's planar or not planar, right? For Dijkstra's and algorithm.
Yeah.
Yes, sir. Okay.
So the two conditions must satisfy. The edge weight should be positive, and there can't be any negative edge weight if you use Dijkstra. If you use Bellman-Ford, there can't be any negative edge cycle, but negative edge weights are possible. If you use Floyd-Warshall, it is same to Bellman-Ford. Negative edge weights are possible, but negative edge cycle are not possible. So negative edge cycles are not possible in any shortest path problem, because if we have suppose a cycle C1, C2, C3, if there's a cycle here and the cycle gives us -1, if you go this cycle again, so the shortest distance between them is -2, it will be -2. If you travel again, it will be -3. Like we can just go on forever and get a really smaller number. Okay, in that sense, there is no shortest path between. There is no sense in talking. There is a shortest path. So everyone get it? Why it is not possible for a negative cycle?
Yes, sir.
Yes, sir.
Yeah.
So
So in
in
this,
this graph also, if we replace C4 position with C3 and interchange the vertices of C3 and C4,
okay.
is that graph right to draw like? Because I don't like that. I
Is
have
that
interchanged C3 here and C4, the places of C3 and C4.
okay?
So in that case also we'll get the same answer.
No, see, if you put C3 to C4, there is a direct edge from C0 to C3 of weight 4, right?
Ah,
Correct?
yes. So this
Yeah.
is the only possible way to draw the graph.
No. See, the graph, you can put the vertices anywhere. You can just put it like, it must not be in this shape alone. See,
Yes.
just a, see, you can just put it like this one also. Okay, this is C1. Let's take, so C naught is there, right? So C naught, C1, C2, C3, C4. Okay, so basically the adjacency matrix, what it says there is an edge between, just a minute, I'll just look at it. So there is an edge between C naught and C1, there is an edge, right?
C2. Yes, yes.
C naught and
C1.
C1 and C naught and C4, right? So these
Yes.
two must be there, and for C1 is connected with C3 also, right? C1 is connected with C3 also, and then it is connected with C2 also. Okay, and then what about the C3? C3 is connected with what? C1, C2, and C4.
Yes. 9.
C1, C2, and C4, right? And then what about the next one? So
C4. C1.
C4 is connected with what? C3,
C0. C0.
C3, C2, and C0, right?
Yes.
Yeah, you can draw it in any way. So the shape is not important, but all the edges which are being mentioned in the original graph should be there. That is the important point. Okay.
Right. Right.
Yeah. So this will be the graph basically, and the shortest distance between C0 and C3 is 6 in this case, and the total pair would be 6,000. Okay, we'll just go to the follow-up question. Yeah, this is the same adjacency matrix which is given. Okay, so see, if an inspection team member wanted to inspect all the branches of the company's, see, okay, we'll see. It's not the same graph, I guess. It's a different graph. Okay, so another adjacency matrix is given. A company has branches in each of 5 cities, C0, C1 till C4. Okay, the fare for a direct flight from CI to CJ is given by same IJ entry, and this is the following matrix. Okay.
That's the same graphs.
Okay, it is the same adjacency matrix which is given. Okay, so the graph also will be same. So, but the question is new. If an inspection team member wanted to inspect all the branches of the company, starting from C0, so you want to start from C0 and ending at C3, visiting each branch exactly once, then which route should he choose in order to pay minimum fare for this flight? And a sample example is given. If your route is from C0, C1, C2, C3, C4, then enter C0, C1, C2, C3, C4. And it is also clearly mentioned that you can visit a node only once. Okay. For example, like you can't like come here and again come back to C2 and C4. Okay. So
Yes, sir.
C0 to C3, if you come, you have to go to C3 to C4, not again to C3 to C2 and C2 to C4. Okay.
Yes,
Yeah.
sir.
So yeah, if you get an answer like this one, just post it like this on the chat box. So the graph would be same now. So I request everyone to try it. It must be, this route must be such that the total flight fare should be minimum. Okay.
Should we use Bellman-Ford's here?
Sorry.
Should we use Bellman-Ford's algorithm here?
See, so it is negative. You can use Dijkstra also, but this is slightly different question which is asked. If you read this question carefully, then you will get it.
Because we need to find like from every vertex to another vertex whether there'll be a shorter path. I think.
No.
Oh, okay. It has to start from C. Okay. Yes,
It
got
is
it.
starting from C0 basically,
Yeah,
and
sorry.
it,
Yes.
okay. Just read this question carefully.
Yes.
Like this is like if you use some direct formula, I don't think like you will get the answer. So you just have to do some work in this question. So we have to connect all the vertices, and then we have to visit each vertex just once. It is not asking the total cost, which is it is not asking about the total cost. This is asking about the order of vertices which we are visiting. Yeah, you can also put the total cost if you get it. Yeah, you guys are getting the answer, but check which one of that is minimum. So we need the minimum flight fare. Okay, so you can just add all the cost. Suppose you get C1, C2, C3, I mean C0, C1, C2, C3, C4. Just add all the path weights, I mean edge weights. You will get some number. So that should be minimized. Okay, so if we get a sequence, just check are there any other sequence such that the total value is minimum. Okay. And you have to write the answer in such a way that the total edge weights of the given path is minimum. So can we discuss the solution now?
Yes, sir.
Yes.
Yeah. Since we get the same graph, so there is no much work here. We'll see. So this is the graph now. So yeah, we have drawn the graph and it is same as the previous question. So the inspection team member starts from C0 and ends at C3. In between, he has to travel C1, C2, C4. Okay, try to explore all other possible paths starting from C0 to C3. Identify the path that contains all the vertices. There can be more than one. If you can see this is one possible path. C0 to C1, C1 to C2, C2 to C4, and C4 to C3. Okay, and this is C0 to C4, C4 to C2, C2 to C1, and C1 to C3. Okay, these are two possible paths. Okay, now we are going to add the edge weights. So if we choose the first path, this green one, we'll get, if it will be 2 plus 3 plus 5 plus 10, which is 20. If you choose the red path, what will happen? It will be 4 plus 5 plus 3 plus 9, which is 21. So the minimum of these two is 20. So the correct answer would be C0, C1, C2, C4, C3. Okay,
Yes.
and the answer would be 20,000 basically. So everyone got this question?
Yes, sir.
Yeah, got
Yes,
this
sir.
question. So, are there any doubts?
Yes.
No, sir.
Okay, so can we proceed to the next slide now?
Yes, sir.
Okay.
Okay. So yeah, so this is the correct answer: C0, C1, C2, C4, and C3. So now we'll see Bellman-Ford algorithm. This algorithm is used to find the shortest path from a source vertex to every other vertex. It is similar to Dijkstra, but there's a change here. It works for both negative and positive edge weights, and it is not applicable for graph having negative weight cycles. Okay, so negative cycle is not possible, but negative weights are possible. Okay, so now we'll see the algorithm. So we'll see dj is the minimum distance known so far by the vertex. So we'll just initially assume like these, since the just in the matrix or list will be given, we can just draw the graph, and dj is the minimum distance known so far. So that will be the distance will be known, and we'll initialize d0 to 0. Okay, if j is 0, otherwise dj is infinite. So first initially we'll just mark this one 0 to 0. Okay, if j is 0, for another rest will be marked as infinity, and we'll repeat it n minus 1 times. We'll repeat these two steps n minus 1 times for every vertex j is equal to 0, 1 to n minus 1. For each edge j comma k belongs to e, dk will be minimum of dk or minimum of these two, dk or dj plus w of jk. We'll see what it is now. Just a minute. See, for what values of x can we use the Bellman-Ford algorithm to find the shortest path from a source vertex to every other vertex? So yeah, we'll just see what is Bellman-Ford the algorithm in the next question. But before that, we'll just solve this question. So you can solve this question, right? So what can be the possible values of x? We have just saw a similar question, correct?
Yes, sir.
Yeah. So we'll solve this and we'll see how to approach the Bellman-Ford, like how to use the algorithm. So we know the properties of Bellman-Ford, like there can be negative edge weights, but negative cycle is not possible. So using that concept alone, tell me what can be the possible values of x. So this is an easy question, right?
Yes, sir.
Yeah. Okay. See, we can clearly see that all the edge weights are possible in this positive in this case. And can you tell me, are there any cycles here?
Only one cycle, sir.
Yeah, what
One,
is
four,
Kruskal?
two.
Yeah, 142 is the only one cycle, right? There are no other cycle, and we know that the edge weight can be negative also, but negative cycle is not possible. So basically what it is 4 plus 3 plus x should be greater than or
Zero.
0, right? It should be greater than 0, right?
Yes, sir.
Yeah. So 4 plus 3 plus x should be greater than 0. So 7 plus x is greater than 0. So x is greater than minus 7, correct?
Yes, sir.
Yes,
Yeah.
sir.
So yeah, we'll see. Recall Bellman-Ford algorithm is not applicable for negative weight cycles. Note that after n minus 1 iteration, the shortest path value doesn't converge. It basically means is after we perform n minus 1 iterations of Bellman-Ford, if we get new values, like it is not same as the, if suppose basically what I'm trying to say is, if the nth iteration is not same as n minus 1th iteration, then we can also say that there is some negative edge cycle is there in the graph. Okay.
So
If
I have a doubt.
yes,
So why can't it be equal to -7? Then the cycle will be 0, right? It's still not negative.
it should be like positive, right?
So, but it should be non-negative, right? They didn't say it should only be positive.
Yeah, but basically what we'll just assume that it is greater than 0. You're getting it?
Sorry, sir, there was some disturbance from somewhere else.
See,
Could you
we
please-
just assume that this cycle is greater than 0 basically. Okay.
Okay.
Yeah.
Sir.
So that's why we are coming up with x should be.
वही मैथ्स में कोई आदमी नहीं है क्या? सब लोग एनसी पैक चल गए क्या? मैथ्स वाला?
Okay. So this should be greater than -7. So the possible values can be -7 to infinity. Okay. So that is the correct answer in this case. And what this means if there is a negative cycle after nth iteration will not be same as the n minus 1th iteration. We'll see what that is right now. Okay, so let's take this graph as an example. Okay, suppose the source vertex is 0. So since Bellman-Ford also has a source vertex, we are now starting from 0. We need to perform the Bellman-Ford algorithm up to 3 iterations. Now I'll show you how to solve this till 3 iterations. I think the question will be to solve it till how many iterations? So how many iterations are possible in this case? Like how many we should do? Can someone unmute and tell me? 6. Is it? How many total of vertices are there?
7.
8 vertices.
8 vertices.
8.
So we have till n minus 1. Okay.
Six.
So 7 times we have to do the iteration. I'll show you how to do the first 3, and then you can proceed further. So what we'll do, this is the initialization. So we'll just initialize 0 to 0 and the rest all to infinity. So that is the first step in the algorithm, right? Hello?
Yes, sir.
Yeah. And now in the second step, what we'll do, we can see where we can go from source 0. Because since this is infinity, we don't have any clue about this one. So this is known. So from 0, we'll see where we can go. We can go to where? From 0?
1.
1 we can go.
4.
So 0 to 1 will be what? 10, right?
10.
So this will be 10 will be here. And then where else we can go?
4 and
4.
7.
4, right? So 0 to 4 will be 4. So here there will be 4. Here there will be 4. And then where else we can go from 0?
7.
7, right? So it will be 6. So here we'll get 6. So here we'll get 6, here we'll get 4, and here we'll get 10, right? And the rest, everything would be
0.
Infinity.
Infinity.
It will be infinity. Okay. See. So this will be 10, 4, 6. Okay. This is the first iteration. Okay. Now we'll see the second iteration now. So see, since we know that from 0 to 1 we can go in 10, and 0 to 4 we can go at 4, 0 to 7 we can go at 6. So what we'll do, we'll see from 0 to 1, and now from 1 where else we can go, we'll see. Okay.
Yes,
From
sir.
1 where we can go?
2.
1 to 2 at 1
1.
distance. So, but we need to, since this is 10, so 0 to 2 would be
7.
7.
11, right?
Yes, sir.
Yes, sir.
Yes, sir.
10 plus 1, which is 11 here. Here there will be 11. From 1, we can't go anywhere. We can just go to 2, correct?
Yes.
Yeah,
Yes.
so the change would be this 11. So from 0 to 4, we can go. From 4, where we can go?
We can't go anywhere, sir.
Can't go anywhere, right? There is no outgoing edge. Okay, so the next thing we'll see, from 0 to 7, we can go in 6 units. From 7, where else we can go?
6.
7 to 6. So what will be the distance?
-2. -2 plus 6. So it will be
4.
6 minus
Minus 4.
So we have to calculate from 0. Okay, so 0 to 7 is already 6 here. So from 6 we can go here in -2 units. So 6 minus 4 would be, 6 minus 2 would be 4 here. Okay, so in 6 it will be 4, and 7 it will remain 6 as it is, and 4 it will be 4, it will remain as it is. 2 will here change from infinity to what?
1.
Sorry?
1.
11.
11.
Okay, it will not be 1. Okay, so from 1 we can go to 2 at 1, but we are asking from 0. So 0 to 1 it is 10 and 10 to 1 it is 1. Okay, so this will be 11 here and this will be 10, it will remain as it is, and this will be 0. So can someone tell me what will be the next iteration values? Here what the value will be?
0.
0.
What is the
10.
value here? 10. Okay, what is the value here?
11.
11.
How 11? 0 to 1 and 1 to 2. Okay, so here there will be 11. So what is the value here?
Infinity.
Correct. So what will be the value here?
4.
4. It will remain same. What is the value here?
Infinity.
It will be again infinity. So what is the value here now?
4.
4.
4, right? So which is 0 to 7 and 7 to 6. So it will be 4 here. So what is this value?
6.
6.
It will also remain as it is. So this is the second iteration that we'll get. Okay, correct. So now
Yes, sir.
we can see there is 2 more things which are added. So 0 to 2 we have find a new 0 to 2 we have find another path, and also 0 to 6 we have find another path. Okay, so we'll see from 0 to 6, from 0 to 2 we can go in 11 units. From 2 where else we can go?
We
From
can
2
go to 7.
7 and we can go to 5, right?
Yes.
Yeah, first we'll see what happens if we go to 5. What will happen if we go to 5?
1.
11 minus 10. 1.
11 minus 10 will be 1, right? So 5
Yeah.
here there will be 1. If we go to 7 here, what will happen? 11 minus, what will happen if we go to 7?
3.
3.
3, sir.
7 minus 8 would be 3, right? But already what is here?
6.
6.
6 is here, right? Which of these two is minimum?
3, sir.
3.
3.
So this will change from 6 to
3.
3.
3.
okay. So this is a point which we should be noting it. So from 6 it will be 3. So again now, so what is the other thing? The new path which is discovered, we can go to 6 in 4 units, right? From 6 where we can go?
3.
3,
6 we can go to 3 in how many units?
4.
8, sir.
Sorry, it's not 4.
8.
3, sir.
8.
From 6 to 3 is 4,
Oh.
but we are traveling from 0 to 3, right? So 6 is already 4. So
4.
4 it will be 8. Okay.
Yes, sir.
Have everyone noted down in a paper? So what will be the value? This will be 0.
0.
0.
Correct.
10.
This will be 11 as it is. What is the new value that we got here? 0 to 3.
8.
8, right? Yeah. This will be 8. So for 0 to 4, it will again be 4 only. No change.
4.
What is the 5 we got the value as?
1.
1.
Correct. So what is the value we got for 6?
4.
It is 4 as it is. So what is the new value that we got for 7?
3.
It will be 3 instead of 6. Okay.
Hmm.
The updated value that we can see is this one. Okay. Yeah. So yeah, we'll just see. So everyone got it how to do this iteration and all?
Yes, sir.
Yes,
Yes.
sir.
Okay. So yeah, it is the same graph. So we have to find what are the values of D3, D4 and D5. For example, we have to do all the 7 iterations. Okay. And then find what is the minimum distance from 0 to 3, 0 to 4 and 0 to 5. That is what it's asking. Okay. You got this question?
Yes, sir.
Yes, sir.
So we had to do 7 iterations, no? So why we did only 4?
This is an example we did. So you have to do all the other iterations.
Okay.
This is an example we talked. So I've just explained how to do the iteration right now. So from this, you guys have to continue and do till 7 iterations. And after getting 7th iteration, suppose let us assume the value to be same. Then D3 is 8 in this case and D6 is 4 in this case. You have to do it as it is. Okay.
Yes, sir.
Yeah. Do the 7 iteration and you will get the value here and write the corresponding value to D3, D4 and D. Okay.
Yes, sir.
Yeah.
So can you show the tables of one more second?
Yeah, sure. This is still third iteration. You can also check, like if you do the 8th iteration, the value of 7th and 8th would be same. 7th iteration and 8th iteration, it will just converge, okay, after 7 iterations, because there are no negative cycles in this graph. If it doesn't converge, then we can say there are some negative cycles, okay. Yeah, the answer which you gave is correct.
So could you go to the question slide?
Yeah, is the question visible?
Yes.
Yes, sir.
Yeah, I got the answers are correct, but I got very few. Yeah, but we also got different answers. So you guys need more time, or shall we discuss this?
Discuss.
Discuss.
Sorry.
We can
Discuss.
discuss.
Okay. So yeah, I'm going to discuss the solution now. We can see the fourth iteration. So fourth iteration will get 0, 10, 11, 8, 4, 1, 1, 3. So yeah, we can see from the third iteration. So 0 to 3, there is a new one, 8, 8, 1 and 7. So from here we'll see from 3 where can we go, and from 5 where can we go, and from 7 where can we go. Okay, with the new H weight. So if we do that, we'll come up with this solution. Okay, so this will
6 will
be,
be 2, right, sir?
sorry.
6 will be 2, right, sir? From 5, we are going to 6. 5 was 1. And
Yeah,
1 plus 1 will be 2, right?
7, 3, 3
see,
minus
but
2 will be
see, yeah, this will be 2. But if you go from 7, 7 has a new weight which is 3, right?
Okay.
From
Yes.
7 to 3, it will be 7 to 6, it will be 3 minus 2, which is 1. Here you will get 2 only. First, if you just got it as 2, but now if you go from here, it will be 1. So we have to choose the minimum. So that would be 1. Okay. So you got it? Hello?
Yes, sir.
Yeah.
Yes.
So this will be 1, and the rest will remain same. If you do another iteration, like 6, now we can go at 1 unit itself. So from 6 only we'll see, we can go to 3 alone. So 6 to 3 is 1 plus 4, which is 5. Before it was 8, now it was 5. We'll just put the minimum value in that case. So the answer would be 5. Okay. So only this will change. If you go to the sixth iteration, so now 0 to 3, we can go in 5. So from 3, we'll see where we can go. Okay. So from 3, we can go to 4 and 2. So if you go to 4, this will change, correct? So it is 5 minus 3, it will be 2 now. The new value will be 2. So and the seventh iteration will be same as this iteration. Okay. So from 4, we can't go anywhere. So nothing will change. It will be same as this one. Okay. So this is the final value now. So what are the questions? D3, right? D3 would be 5, D4 would be 2, and D5 would be 1. So everyone got this solution?
yes, sir.
Yeah. If anyone of you don't get it, you can just ask me. I'll explain it once again. Or can I proceed with the next question?
So you can proceed with this.
Yeah. Okay. Now we'll see Floyd-Warshall's algorithm. So it is used to compute all pairs shortest path. So it will give us the shortest path between any two vertices. It is applicable for directed weighted graphs of both negative and positive edge weights. It is similar to Bellman-Ford. It will work for negative edge weights also, but no negative cycles are permitted. Okay, not applicable for graphs having negative weight cycles. Okay, so yeah, so SPK of I comma j is the length of the shortest path from vertex I to j using the vertices 0 to k minus 1. Okay. So we'll see what it is. For example, if we compute SP3, it means we need to find the shortest distance from any vertex I to j via only 0, 1 and 2. Must travel via 0, 1 and 2 only. Okay. If no path between the vertices, then simply write it as infinity. So we'll see what it is. See, suppose this is a given graph. So SP0. So what we have to do, we have to write only the values which are passing through 0 only. Okay. So from that we'll see from 0, we can go to 0 to 1. So it will be 1. We can't go to any other vertices from 0, right? So the rest will be infinity. If you see from 1, we can go to 3, right?
3.
Yeah.
Yes.
It basically SP0 would be the original adjacency matrix of this graph only. Okay.
Yes, sir.
Yeah.
Yes, sir.
So this is just the adjacency matrix of this graph. So we can see from 1 to 3, it will be 2, and 1 to 4, it will be -1 again. And from 2 to 0, you can see 2 to 0, it is -4, and 2 to 1, it is 3. And then there are no other outgoing edges for 2. If we see for 3, there are no outgoing edges, so everything is infinity. For 4, you can see there are 2 outgoing edges, 4 to 3 and 4 to 2. So it will be 4 and 3 respectively. Okay. So yeah, we'll now see an example. So we'll see what is SP3 now. Just a minute. Yeah. See, SP3 means we can travel via 0, 1 and 2 only. Okay. Hello.
Yes, sir.
Yeah. We can go via 0, 1 and 2 only. See, from this we can see that SP3 0 to 1 we can go because it is traveling via these 3 vertices. So 0 to 1 would be 1 only. We can go to 0 to 0 to 3 like in SP 0 to 1, like we can go to 0 to 1 and 1 to 3, right? It will be 3
Yes,
again.
sir. Yes, sir.
So 0 to 4 we can see 0 to 1 and 1 to 4, correct?
Yes, sir.
Yeah. So this is the start and end vertex. 0 is starting and 4 is ending. We can see only the intermediate vertices can only be 0, 1 and 2. Okay. So there can't be any other intermediate vertices. We have to travel via 0, 1 and 2 only. And we can see from 1. From 1 we can't go to 0, correct? Like 1 we can go to 0 via how 1 to 4, 4 to 2 and 2 to 0, right? But 4 can't be an intermediate vertices, correct?
Yes, sir.
So from 1 we can't go to 0 in SP3. Okay. From 1 we can't go to 1 again. Okay. So because to travel to again 1, we have to go to 1 to 4, 4 to 2 and 2 to 1. Since 4 is again an intermediate vertices, it is not possible in this case, SP3. Okay.
Yes, sir.
Yeah. So 1 to 1 will be infinity again. So 1 to 2 we'll see 1 to 2. 1 to 2 also 1 to 2 is also not possible. So 1 to 3 we can directly go, correct? So it is 2. We are writing 2 here. 1 to 4 also we can directly go. It is -1. So we don't got this till now.
Yes, sir.
Yes, sir.
Yeah. So now we'll see for 2. 2 to 0 directly we can go, and 2 to 1 also we can go directly. So it will be -4 and 3 respectively. 2 to 2 we can't again come back with only using these 3 as the intermediates. So it will be infinity only. So from 2 to 3 we'll see. From 2 to 3 we can go 2 to 1 and 1 to 3, or 2 to 0, 0 to 1 and 1 to 3. We have to find which is the minimum distance here. So if you go to 2 to 1 and 1 to 3, the total distance is 5. But if you go to 2 to 0, 0 to 1 and 1 to 3, what happens? It is -4, -3 and -1, right?
Yes, sir.
Yeah. So
Yes,
this
sir.
will be -1 here. And now we'll see 2 to 4. 2 to 4, you can go to 2 to 1 and 1 to 4. Or again, you can go to 2 to 0, 0 to 1 and 1 to 4, right? So we'll again find which one of this is minimum. So obviously this will be minimum. 2 to 0, 0 to 1 and 1 to 4. So 2 to 1 we can go in -3 units. And here 1 to 4 will be again -4 units we can go. So 2 to 4 is -4. So everyone got this?
Yes, sir.
Yeah.
So
From
one doubt I have. Uh, Sir, why 2 to 1 is -3?
2 to 1 here there is a direct edge 3, but we are finding the shortest distance. So 2 to 0 is -4 and 0 to 1 is +1. So 2 to
Okay,
1
okay,
instead
sir.
of going this route, we'll take this route. So it will
Okay,
give us -3. Okay.
yeah, yes.
Yeah. So from 3 we can't go anywhere. There are no outgoing edges. So everything will be infinity here. So from 4 we can see. From 4 we can go to 2. So 4 to 2 is possible. 4 to 0 we can see. We can go from 4 to 2 and 2 to 0, right?
Yes, sir.
Yeah. 4 to 0 we can go. 4 to 2 and 2 to 0. So this will be 0. 4 -4. And we can see from 4 to go to 4 to 1, we can go from 4 to 2 and 2 to 1. So see, 4 to 2 and 2 to 1 also we can go. Or again we can go from 4 to 2, 2 to 0 and 0 to 1. So which one of those two is minimum? Obviously the second one, right? 4 to 2, 2 to 0 and 0 to 1. Correct?
Yes,
Yes,
sir.
sir. 1.
Yeah. So that value will be 1. And if you can see, we can also go from 4 to 2. 4 to 2, we can go in the distance of 4 units. And also we can go to 4 to 3. Why we can go to 4 to 3?
We can, it is
Using
direct.
one,
Yeah,
Direct.
using two
it is a
zeros.
direct edge. It is a direct edge. Okay, there are no intermediate vertices. Okay, the intermediate vertices should be 0, 1, and 2.
0, 1.
Yeah, since there is a direct edge, we can directly go. Okay,
Yes.
yeah, and 4 to 4, how it is 0?
You, using the cycle, sir.
Yeah, 4 to 2, 2 to 0,
2 to 0,
0
0
to
to 1, 1
1.
to 4.
Okay, so 4 to 4 is 0 in this case. So everyone got how to calculate sp3?
Yes, sir.
Yes, sir.
Yes, sir.
Yeah. So
Sir, I have question here.
yes,
Why we have taken only vertices 0, 1, 2?
that is the
0, 1,
algorithm. sp3 means we can go via 0, 1, 2 only. If sp4 is given, we can go via 0, 1, 2, 3. Okay.
2. Okay. Means
The
80 graph. If the graph will change, that is not
Yeah.
matters.
Basically, we are assuming that the graph is named from 0 to n minus 1. Okay.
Oh,
The vertices are named from 0 to n minus 1. 0, 2, 3, and all. Okay.
okay.
Yeah. So sp4 means it can travel via the intermediate things can be 0, 1, 2, and 3 also. Okay. That is what the algorithm says. Just a minute. Yeah. From this point, you can see spki of j is the length of the shortest path from vertex I to vertex j using vertices in 0 to k minus 1. Okay. So if this is 4, we can use from 0 to 3. Okay.
Okay, got it, sir.
Yeah. If there is no path between the vertices via this vertices, then it will be assumed as infinity. Okay. So which of the following possible is sp4 use Floyd-Warshall algorithm. Okay. So as I said again, 0 to we can use 0, 1, 2, and 3 as the intermediate vertices. 4 can be in one of the intermediate vertices, and then calculate sp4. Okay. So can we discuss the solution for this one? I think everyone got the correct answer.
Yes, sir.
So yeah, we'll see what is SP4 in this case. So we can travel via 2, 0, 1, 0, 1, 2, and 3 as the intermediate vertices. So yeah, we can see from SP3 also and then draw the SP4. So 0 to 1 will be 1 and 0 to 3 would be 0 to 1 and 1 to 2. Okay, so it will be 3 and 0 to 4 will be 0 to 1 and 1 to 4, which is 0. And if you can see 1 to 0, you can't go from 1 to 0, correct? We have to use 4 also via the intermediate vertices to go to 0 back again. So since
The SP5 no, sir.
SP5 exactly. Okay,
Okay.
it must be SP5. So since we can't use that, this will be again infinity only, and we can't again come back to 1 and 2 also. So those will be infinity. We are allowed to do that only when we can include 4. So it will be on SP5. So since these three are again infinity, so we can go from 1 to 3, which is 2 units, and 1 to 4 also we can go. 1 to 4 we can go by 2 paths. 1 to 3 and no, there is only one path, so there is no outer resistance. So see, we can go from 1 to 4 via this path, which is -1. Okay, and we'll see for 2. 2 to 0 we can go. 2 to 0 we can go in -4 units, and 2 to 3, I mean 2 to 1 we can go in -3 units. So 2 to 0 and 0 to 1, which will be -3 again. So 2 to 2 we can't come again because we have to use 4 as an intermediate to come back to 2 again. So since we can't use 4 as an intermediate path, it is infinity here. So 2 to 3 we'll check. 2 to 3 is 2 to 0, 0 to 1 and 1 to 3, which will be -1 in this case. And 2 to 4 would be 2 to 0, 0 to 1 and 1 to 4. Correct?
Yes, sir.
Yes.
Yeah, it will be -4. So from 3 we can't go anywhere. There are no outgoing edges. So this will again be minus infinity only. So for 4 we can see 4 to 3 we can go in 3 units. 4 to 3 we can directly go in 3 units. And 4 to 0 we can see +4 and -4 it will be 0. And 4 to 1 is 0 plus 1, which is 1. And 4 to 2 is directly 4 units. And 4 to 3 we can see directly go in 3 units. And 4 to 4, like we can form this cycle and again come back in 0. So this is the correct option. This is the SP4 of this given graph. Okay.
Yes.
Yeah. Can we go to the next one? I think the
Yes,
minimum
sir.
cost spanning tree is left. Okay, so
Yes.
they're asking what is SP5 again. Okay. So I'll just give you just 5 minutes to calculate SP5. It is just a similar concept. Now we can go via all the vertices 0, 1, 2, 3, 4. Okay. So it is similar to the previous one. So what we'll do, we'll just discuss the answer in like 5 minutes. But if you want more time, just let me know.
Yes.
Yeah, that is the correct answer. So can we discuss the solution now for this one, or you guys need more time?
So I think it's
Also, we can
done.
discuss.
Yeah, like we have 2 more topics to cover. So we'll discuss the solution. Is it fine?
Yes, sir.
Yes, sir.
Yes.
C is again correct. So it is just same thing. But now we can go to 4 also. So from that you can see from 0 to 0 to 0, correct?
Yes, sir.
Yeah, we can use this one, 0 to 1, 1 to 4, 4 to 2, 1, 2 to 0. So this will be 0. Okay, and then 0 to 1 we can see is 1, and 0 to 2 we can see it's 4, right? 0 to 2,
Yes.
it will be 0 to 1, 1 to 4, and 4 to 2. Okay, and 0 to 3 would be 3. Okay, so 0 to 1 and 1 to 3, and 0 to 4 would be again 0. And we can see for this one, 1 to 0. 1 to 0 is minus 1. So we can go to 1 to 4, 4 to 2, and 2 to 0. Okay, so it is minus 1. And 1 to 1 we can get it as 0. So we'll just again form the cycle and we'll get 0. And 1 to 2 we can get it as 3, right? Minus 1 plus 4, which is 3. And 1 to 3 we can get it as 2 only, direct edges there. And 1 to 4 we can get it as minus 1. So yeah, this is also direct edge, so it is the minimum also. So similarly we can calculate for the rest one, right? Are there any doubts in how to calculate this one?
No, sir.
Can we go to the next concept now?
Yes, sir.
Okay. So now we'll be discussing what is minimum cost spanning tree. What is a spanning tree? Spanning tree of an undirected graph G is a subgraph that is a tree which includes all the vertices of G. Okay. So it is a subgraph of the graph, and the subgraph is also a tree. And the tree includes all the vertices which are there in the G, graph G. Okay. So how spanning tree different from a tree? Spanning tree is a subgraph of G, and the subgraph should be a tree. Okay. It is the subgraph of G, the original graph G, and that subgraph should also be a tree. And what is the cost of the spanning tree? It is nothing but the sum of the weights of all the edges in the spanning tree. Suppose a spanning tree has a edge weights of 4, 5, 6. Okay, so the cost of the spanning tree is 4 plus 5 plus 6, which is 15 in that case. Okay, that is
Yes,
the
sir.
cost of the spanning tree. What is the minimum cost spanning tree? So a graph can have multiple spanning trees. Out of that, we'll just select which of the total cost is minimum. Suppose there are 3 spanning trees which have the total cost as 7, 4, and 3 respectively. So minimum cost spanning tree is a tree such that the total edge weight is 3. Okay. So how to find the minimum cost spanning tree? We'll use 2 algorithms, Prim's and Kruskal's algorithm. Okay. Can we proceed further now?
Yes, sir.
Sir, can
Yes.
we only use for undirect graph or
We'll be discussing for undirected graph in this case. Here, we, like right now, we are discussing for undirected graph. Okay. Yeah, we'll see. This is a graph G. So we have to find a subgraph which connects all the vertices. So these are the 3 possible subgraphs, right? 1, 2, and 3. Hello.
Yes, sir.
These 3 are the possible subgraphs which connect all the 3 vertices, right? Okay.
Yes, sir.
Yeah. So these are the possible spanning trees. So suppose let's assume, okay, we'll just study further right now. So see, Prim's algorithm is used to find minimum cost spanning tree of a given graph having n vertices. So step 1, we have to we are incrementally building a minimum cost spanning tree of G. So what we are doing is, let's say the tree vertices is 0, null set, and the tree edges is also 0, which is null set in this case, where TV is a set of tree vertices added to the minimum cost spanning tree, and T is a set of edges which are added to the minimum cost spanning tree. So what will happen? The third step is choose the minimum edge weight, weight of the edge E, I to J. Okay, set the T vertices of the T to I to J, and the edges E. We'll repeat it n minus 2 times and choose the minimum edge weight F is equal to UV such that U belongs to TV and B does not belongs to TV. Add B to TV and F to T. We'll see what this algorithm means. See, just a minute. This is a weighted graph of 7 vertices, okay, which is represented in the following adjacency matrix. If we perform Prim's algorithm with the starting vertex as R, then the order in which the vertices will be added to the set E is. Okay, so directly a question is given. Okay, just a minute. Okay. My board is visible, right?
Yes, sir.
Yes, sir.
Okay. So let's assume like we are starting from this is A. We'll say this is B. C we'll say. Let's take this is 2. This is 4 we'll take. And we can also like take this one as, we'll just take it as 5. Okay. And we are starting from A. Okay. Hello.
Yes,
Yes,
sir.
sir.
We are starting from A. Okay. This is the starting node. So first we have to check from A where we can go. What are all the possible vertex we can reach from A? Hello.
B and
B and
C.
C.
B and C.
Okay. So B and C we can reach. Which one of these two is minimum?
B.
B.
B, right? So the
Yes.
first thing which will be added, we'll just add A in this case first. So A will be added, okay, to the three vertices, correct? And what is the edge? Edge will be AB, right?
Yes.
Yes, sir.
Will be AB, first thing that will be added, okay? So now we have gone to B, correct? And now from B we can go to C and A, and here we can go to what? A, from A we
C.
can go to C. So which of these two has minimum weight?
A to C.
B to A.
No, B to A is already there, right? A to B and B to A are same, right?
C to A, sir.
Sorry?
A
C
to
to
C.
A or A to C.
Yeah, A to C, right? C. So first,
Yes, sir.
after we go to B, what we'll do, we'll just add B also here, okay? And then we can go from A to C in 4 units, right? So this is 5 and this is 4, right? We have to choose the minimum of these two. So minimum of these two is 4, right?
4. 4.
So we will choose this edge instead of this edge, okay? So
Yes,
what
sir.
C will be added at the last, and the final edge which will be added is
AC.
AC, okay? So you got it?
Yes.
Yes.
So this will be the minimum cost spanning tree of this graph. So this is A, this is B, and this is C, this is 2, this is 4. Okay. So the what is the cost of the spanning tree?
6.
6.
6. Okay. So only this is the minimum cost spanning tree of this graph. Like you can also take these two, but this cost will be 7. Okay. A, B, and
Yes.
B. And you can also take AC, BC, and AC. That will be 9. Okay.
Yes.
But we
Yes.
want minimum. So the minimum is from AB and AC. So this is how we'll use Prim's algorithm. We'll start from the source vertex and then find the minimum distance. Okay.
Yes, sir.
Yes.
Yeah. I'll just share the question now. So again, the adjacency matrix is only given. First, you have to draw the graph for this. Okay. And you have to give me what is the TV. So here in that case, it was A, B, and C, right? Similarly, you have to give me what is the order, P, Q, R, S, T, or which is the order that you're getting. Okay.
Yes, sir.
Okay, I'll do one thing. Like if you want, I'll just also give you the graph. So this is the graph. So we have to discuss one more question and the time is low. So this is the corresponding graph of this. And the question says the Prim's algorithm starting from the vertex R. Okay. So we have to start from the vertex R. So this is the graph given. So now calculate, do the Prim's algorithm and tell me what is the minimum cost spanning tree and what is the edges. Okay.
Yes, sir.
Yeah. So this is the graph given. You don't have to draw the graph. You just apply the Prim's algorithm starting from the vertex R for this graph. I got two answers. One of them is correct. There is a slight change. So shall we discuss the solution?
Yes, sir.
Are anyone still solving? If you're solving, I can wait. So can we see the solution now?
Yes,
Yes,
sir.
sir.
So since this is a graph, we have to see. Just a minute. Yeah. So we'll initialize TV as null and TE as also null. We are starting from the vertex R. So TV will have R in R here, and TE edges is currently null. Okay. Now from R, there are two choices. We can go to U or V, but we have to check go to the minimum one, right? So R we are going to U. Okay. Hello.
Yes, sir.
Yes, sir.
Yes,
So
sir.
R U edge is being added here. Okay, and U is also added to the vertices. After R U will come. Okay, and RU edge is added. Okay, after that we have two possibilities. We can either go to R to B via R to B directly or U to B. So basically, like once we added the edges here, we have to see which of these are adjacent. What are the adjacent edges are there to these two vertices which are added. So U and R are the vertices which are added. So what are adjacent to U or what are adjacent to R? So U as B as adjacent and R as adjacent, but since R is already there, we'll ignore it. So now we can see U as B as adjacent and R also has B as adjacent. From these two, which one is minimum?
R2.
RV.
RV, right? So R to B is minimum, which is 3. Okay. So we'll consider this edge. RV is the edge. Okay. And then, okay, RV will be the edge and B will be added. Okay. Okay. So
Yes,
now we
sir.
see from V where we can go. From V we can go to P. From V we can go to U. But one more thing, it should not form a cycle, right? Since it is a minimum cost spanning tree, cycles are not allowed, right?
Yes, sir.
So even though V to U the edge weight is 5 and V to P the edge weight is 7, even though this is minimum, we will not add this one because it forms a cycle, correct? V, U and R forms a cycle. Therefore, which one we'll add?
VP.
Right? Yeah. So V after V, P will be added and the H will be VP. Okay. Yeah. See, choose the minimum weight that is adjacent to R or U or V. So the minimum weight in this case would be UV, but it is not added to TE because it creates a cycle. So now VP will be the minimum H. Okay, so P will be added to TV and VP will be added to T. Okay, so the TEV will be RU, VP, V and P, and the edges would be RU, RV, and VP. Okay, so now we have to see P also will be added now. So we have to see the adjacent for all these three. So now we'll see the adjacent for P. What are the adjacent vertices of P?
Q and T.
Q and T, right? V is also there, but it is already added to V, so we won't consider it right now. So Q and T are the adjacent one. So which one of those two is minimum?
PQ.
Q, right?
PQ.
Yeah. So Q will be added to the V and PQ will be added to T. Okay. So Q will be added to V and PQ will be added to T. Okay, now we'll see the adjacents of P and Q. So P and Q, we'll see what is adjacent to P now? T only, right?
Yes, sir.
Yeah. What is adjacent to Q? S, right?
S.
Yeah. From this one, which will be added?
PT.
PT will be added or QS will be added?
Yes, sir.
PT.
PQ, sir.
See, now this is the graph, right? Till here we have reached, correct?
Yes, sir.
Yeah. So now there are two choices. PT can be added or QS can be added, correct?
PT has to be added, sir.
Why PT has to be added?
So
What
first we need to, sir, if we go through PTS,
Shortest
then it is
distance
shorter.
to T.
No. See, you have to choose. See, what the algorithm says, we have to find the adjacent of all the red color ones. Okay, right now we can find all the red color one which should not be in TV. Okay, find the adjacents of all the red color one which are not in TV.
Okay.
Okay, see, we
That's
can't
why
have
we.
this is a cycle. So what is the adjacent of T which is not in TV? It is T, right? For P it is
Yes.
T and Q it
Yes.
is S. So these two are the possible candidates right now. Okay, but
Yes, sir.
after selecting the possible candidates, what we will do is we'll find which of these two is minimum. Okay,
Yes, sir.
so which
Yes,
of
sir.
these two is minimum now? 9 is
Yes,
minimum
sir.
or 8 is minimum?
QS.
Yes,
S is 8 is minimum, right?
yes, sir.
8 is from Q to S. So we'll add S, not T. Okay,
Okay, sir.
Yes, sir.
yeah, you will add S right now, not T. Okay, so this will be the new one, and the edge will be QS. In the edges, it will be QS, and the vertices it will be S. So now we can go from S to T or P to T. Okay,
Yes, sir.
correct. So
Yes, sir.
this is the adjacent. So from that we have to choose which one is minimum. Which will be minimum?
Yes, T, sir.
ST only, right?
Yes, sir.
Yeah. So because 2 is lesser than 9, we'll add ST, and the final edge will which will be added to the tree is T. And the the vertex which will be added to the TV is T, and the edge will be ST. Okay.
Yes, sir.
So this will be the final one. TV is RUVPQST, and the edges are RURVVP, PQ, QS, and ST. Okay. So this is the minimum cost spanning tree of this given graph, the green line. Okay.
Yes, sir.
Yeah. So the answer would be R, U, V, P, Q, S, T. So can we go to the next line up? Are there any doubts?
No, sir.
Okay. Yeah. Now we'll find the Kruskal's. What is Kruskal's algorithm? It is also used to find the minimum cost spanning tree of a given graph having n vertices and m edges. Okay. So what we'll do, we'll incrementally build a minimum cost spanning tree. Similarly, we did to the Prim's algorithm. So let E be the edges in the given graph sorted in ascending order. Okay. So we'll just take the original graph and sort the edges in the ascending order of its weight. Okay. So everyone got what is this step?
Yes, sir.
Okay. So we'll initialize again TE to null, where T is the set of tree edges added to minimum cost spanning tree. We'll initialize it to null. Scan the edges from E. So we'll just check one by one in the ascending order from E0 to EM minus 1. So we'll go in this order only. We'll not pick anyone in between. So we'll go in this order, and this is in the ascending order. That is to be remembered. Okay. So if adding EI to TE creates a cycle, we'll skip it. Else we'll add it. Okay.
Yes, sir.
Yeah. So again, this is the given adjacency matrix. I think this is the last question. So you guys want the graph, or you'll just write the graph and then solve it? I mean, you
Give
want
the graph, sir.
so everyone know how to draw the graph from the given adjacency matrix, right? That is not a problem, right?
Yes, sir.
Yes.
Yes. Not a problem, but
It is
Yeah.
the same graph.
Yeah, I think it is the same graph only. Yes. Yeah. So this is the same graph. Use this and find the what you have to find? I think you have to find the T edges. Okay, in this case, you have to find the corresponding edges that should be added. It is not TV, it is TE using Kruskal's algorithm. Okay. For example, the edges should be arranged in 1, 2, 3, 5, 6, 7, 8, and 9. That is the ascending order, and you have to add one by one. Okay.
Yes.
Yeah. You have to give the answer in this format, the one which Jacob gave. Jacob, try again. You have to use Kruskal's algorithm and find the answer. Okay.
Yes.
Yeah. I think you have used Prim's, I guess. You have to use Kruskal's algorithm to find the answer.
Okay, sir.
Okay. So yeah, you have to use Kruskal's algorithm, not Prim's algorithm. Pratap, kindly check your answer. So you have to first arrange in the ascending order and then take every edge and write. Okay.
This also have to be.
The graph is visible, right, to everyone? Hello.
Yes, sir.
Yes, sir. Yes, sir.
So can we discuss the solution now?
Yes, sir.
Okay. Just a minute. Okay. Yeah, we'll discuss the solution now. So
So
first,
1 second.
okay,
So
yeah,
1 minute.
yeah, sure.
Yes, sir.
Yeah. So can we discuss the answer now?
Yes, sir.
Okay, just a minute. Yeah, we'll see. So first we have to arrange this in minimum weight, right? So it will be 1, 2, 3, 5, 6, 7, 8, and 9, right?
Yes.
So first we'll add the least one, which is RU will be added. Okay.
Yes, sir.
After
Yes.
RU, which will be added? ST will be added,
ST.
right?
Yes, sir.
Yeah. After ST, which one will be added?
RV.
RV. Right?
RV.
Yeah. After this, which will be added? BU will be added, but this will form a cycle, right?
Yes, sir.
Yes, sir.
So skip it. So what is the next minimum one? QP.
PQ.
Yeah. QP will be added. And after that, PV will be added, right?
Yes, sir.
Yeah. And after that, QS will be added.
Yes.
Okay. Yeah. And this will not be added because it will again create a cycle, correct?
Yes, sir.
Yes, sir.
Yeah. So that will be the correct answer. So we'll see. So this is the increasing order of the given weights. We'll initialize TE to null set and scan all the edges and start adding it to the minimum cost spanning tree. So first RU will be added. So the graph will look like this one. And then which one will be added? ST, right?
Yes, sir.
Yeah. Then the graph will look like this one, correct?
Yes, sir.
Yes.
After adding ST. And then which one should be added?
RV.
RV, right?
Yes, sir.
Yes.
So the graph will become like this one, correct?
Yes, sir.
Yes, sir.
After this, UV should be added, but it forms a cycle.
Okay.
So we'll ignore it. Okay. So after UV, so we have ignored it here. So PQ should be added, right?
Yes, sir.
Yeah. So PQ will be added again, and then PV will be added. You can see
And then QS.
QS will be added. That's it. Okay. So PT will not be added. It creates a cycle, correct?
Yes, sir.
PT creates a cycle, so it will not be added.
Yes, sir.
So this will be
Yes,
the
sir.
final answer, correct?
Yes, sir.
So these two are not added. So RU, ST, RV, PQ, PV, and QS. So this will be the final answer. Okay.
Yes, sir.
So
Maybe
everyone
it has to be always like that only. So it should never be like a VP or a, PQ. It should not change, interchange.
you should not.
Order, right?
You can say instead of RU, you can say UR also. That doesn't matter. But these two can't be interchanged. Okay. Like for example, ST can't be at the last, or ST can't be at the this one, fourth one or third one. Okay.
Yes, sir.
Okay. Yeah. And once again, like before leaving this meet, I have again posted a G form in the chat box. So I request everyone to fill that before leaving this meet. And now, if you have any doubts, you can ask. Okay. Are there any doubts in the questions that we have discussed today? Hello. Okay.
I have one question.
Yes.
Yeah, for this crucial algorithm, we
Okay.
can only use directed, means undirected graph, or sorry, directed graph. We
This is
can.
an undirected graph, right?
This is undirected graph, right?
Yeah, this is undirected here. See what we have seen. Spanning tree of an undirected graph G is a subgraph. So we are seeing undirected graph here, right? This is undirected.
But that is for prima algorithm.
Even for this one, it is undirected only. See, just a minute. See, this is also same graph, right? This is also undirected, right? Same as that one. As you can see, Q to P is also 6 and P to Q is also 6, right? I think you will get.
I thought that you have give the same question you have given.
No. It is the same graph. The graph is also same. See, this will be P and this will be Q. This will be P and this will be Q. P to Q is 6 and Q to P is also 6, right?
Yes.
And PQR is S to Q is also 8 and Q to S is also 8, right? You can see these two.
Yes.
Similarly, this is also an undirected graph, right?
Okay.
So yeah,
Okay.
we are doing this for undirected graph. So we'll get this one as the answer. So mostly you'll be given undirected graph, okay? So all the time will be given an undirected graph.
Okay.
As far as we are concerned. So yeah, we should first arrange them in the ascending order here and then start adding them such that one of them should not create a cycle. Okay.
Okay.
Okay. Yeah. So are there any other doubts?
Yes, sir. So where do we get the previous year's papers for practice?
Actually, it is not available in your portal, I guess. So there are some groups, right? Opennotes.org or something.
I'm not sure.
You are in some WhatsApp groups or something?
No, sir.
They're not in any WhatsApp groups. Okay, just a minute. Yeah, so yeah, but before leaving, I request everyone to fill the form. The form is working, right?
Yes, sir.
Yes, sir, it's working.
Okay, okay. If you just type like the open notes in Google, you will get some the study materials, I guess. Just go to Google and type the open notes space IITM.
Okay.
From there, you can go and check IITM BS study material. From there also, you can get the question papers, previous year papers.
Okay, sir.
Yeah, and even like you are being assigned to certain houses, right? Even that there are some pages where you can get the previous year papers.
Okay, okay, sir. Yes, thank you so much.
Yeah.
But we've not been actually assigned yet to the house.
Okay, okay. So yeah, like now right now I think you can get it from this one, the open notes.
Sir, please repeat the site what you have told.
Sorry,
What site for papers?
what size means?
Site which site you have told right now for previous year papers?
Site. Okay,
Yes.
it's open notes. OPEN space notes. Just type it in Google. Open notes space. You can just type IITM. Or it is the opennotes.in. But I think you have to log in with your student mail ID or something. You can just check it once.
Sir, it is not working. Please share the link from the link chat box.
I think you guys have received the student mail ID.
Yes, sir.
Not, sir.
See, but actually this is not an official thing. So I say I'm just telling you certain recommendations, but this is not the official thing. So you guys can check the WhatsApp groups, right? So there must be certain WhatsApp group between you guys. Hello.
So we don't have WhatsApp.
Okay.
Yes, sir. No WhatsApp group.
Okay. Just a minute. See, I've pasted it in the chat box. Can you guys see?
Yes, sir. Yes, sir. Got it. Thank you,
Okay.
sir.
Okay. Thank you.
Thank you, sir.
So are there any other doubts?
No, sir.
No, sir.
Okay.
Thank you, sir.
Thank you.
Thank you, sir.
Yeah. Thank you. Yeah. Just before leaving, just fill the form which I've given in the chat.
Yes, sir.
Okay. Thank you.
Thank you.
Thank you, sir.
Yeah. Thank you.